Deep learning produces remarkably intuitive results, like identifying a specific face in a crowd or generating realistic environments. But beneath those capabilities lies a rigid grid of numbers being multiplied together millions of times. The challenge is executing that math efficiently. Training a modern model involves processing millions of parameters across massive datasets, creating a logistical burden that would crash standard systems. That is where TensorFlow comes in. Developed by Google, it's the foundational open-source software framework built specifically to manage all of that heavy mathematical plumbing. This graphic shows the core unit of this entire framework, the tensor. A tensor is a multi-dimensional array of data where every element shares the exact same data type. Tensors scale in complexity. A single value is a rank 0 scalar. A 1D list is a rank 1 vector. By stacking these, we move to a rank 2 matrix and eventually into three-dimensional spaces, representing highly complex information. Looking at this flowchart, we see how TensorFlow handles computations using a data flow graph. The blue nodes, like matmul, represent mathematical operations. The arrows connecting them are the actual tensors flowing from one calculation to the next. There is a strict rule here. Tensors are immutable. Once data enters the graph, you cannot change its contents. Instead, as inputs flow upward and hit a node, TensorFlow performs the operation and generates an entirely new tensor to carry the result forward. TensorFlow provides a robust system for moving data around, but hand-coding every mathematical node and connection for a massive neural network is inefficient. To design the structure itself, we need a higher-level tool. We use Keras. Keras is a high-level API written in Python that runs directly on top of TensorFlow. It acts as the architect, giving developers simple building blocks to draft and test deep neural networks. This diagram maps out the first step in the Keras workflow, specifying the layers. By using a sequential model, we can stack these layers linearly, defining a clear path from the red input layer through the blue hidden layers straight to the green output. If you look closely at the gray lines connecting the input to hidden layer 1, you're looking at a dense layer. Every neuron receives an input from the previous step. These connections carry specific weights and biases the network adjusts as it learns. Building the skeleton is only step 1. For step 2, we give this structure behavioral rules, the activation function, which is the standard choice for hidden layers. Its mathematical rule is simple. If the input is negative, it outputs 0. If it's positive, it outputs the input value exactly. This logic makes computations fast and efficient. At the final stage of the network, we need something different. If we check the math on the right side of this output layer, we see the Softmax activation function. Softmax translates raw final calculations into a clean probability distribution, where all possible outcomes sum to exactly 1. With Keras, we have a physical architecture and the rules for data movement. The network has the capacity to process information, but because the weights are currently random, it has not yet learned anything. That brings us to step 3, compiling the model. To learn, the network must mathematically quantify how far its predictions are from the actual target. This table shows how we measure error, using a loss function. The tool depends on the job. Predicting a continuous number, like a house price, uses mean squared error at the top. Sorting images into categories uses cross-entropy. No matter the equation, the ultimate mathematical objective is identical: drive the result of that loss function down to a minimum. To get that number down, we use optimizers. These are specialized algorithms that look at the loss and adjust the weights and biases back in the dense layers to improve the next prediction. Tracking the W column in this table shows gradient descent at work. It calculates the error gradient and updates parameters in increments. The size of these increments is controlled by the learning rate, driving the numbers toward convergence. Standard gradient descent uses the whole dataset at once, which is slow. Stochastic gradient descent updates the model using randomly selected training examples. This creates rapid, erratic steps to escape shallow local minimums. Modern optimizers like Atom adaptively change their learning rate, calculating momentum to accelerate down steep slopes and brake precisely at the bottom. Using an efficient activation function like ReLU, combined with a modern optimizer, prevents the gradient from disappearing. Without this specific combination, the error signals would shrink to zero, causing the training process to stall. TensorFlow formats the data, Keras builds the frame, and mathematical optimizers drive the refinement. This pipeline turns raw software architecture into a system capable of iterative improvement.